Our next speaker is Dr. John Kokarakis from Veritas. John will be speaking about waste heat recovery and slow steaming.
Thank you, Mr. Chairman. Ladies and gentlemen, good evening. Congratulations are due to SQE for putting together, once again, an excellent forum. This presentation is motivated by agonizing questions on the adequacy of the exhaust gas boiler to produce steam under part-load operating conditions like the ones that we encounter in slow steaming. My predecessor talked about the legal aspects of slow steaming. About law, I will talk about order in slow steaming. It is well known that, and is indicated in this so-called energy balance Sankey diagrams, that about 50% of the energy in fuel is wasted in the form of thermal energy in exhaust gases and cooling water, in the jacket and scavenged air coolers. The primary candidate for further utilization and improvement of energy are the exhaust gases. The reason for that is that it is proven that the quality of energy in the exhaust gases, the exergy as it is called, is higher in exhaust gases compared to the others. Incorporation of waste heat recovery systems increases the efficiency to about 55%. This is a very good number compared to what we are used with steam turbines of the past. Of course, there is no free lunch, so we notice a slight reduction in the efficiency of the engine because of increase of pressure drop in the system and a slight reduction in the scavenged air pressure. The centerpiece of an exhaust gas system, of course, is the exhaust gas boiler, downstream the turbocharger and the exhaust gas header. Potentially, at part load, at slow steaming conditions, we bypass this boiler to avoid passing the gases at low speeds, which is not very healthy for the boiler. Just basics, there are two types of exhaust gas boilers. The most popular one on the right side, water tube boiler, and the smoke tube boiler. The water tube boiler actually has no steam drum. It has risk of fire, high risk of fire and soot deposition, and it needs soot blowers for cleaning. The smoke tube boiler has the tubes surrounded by water and has lower risk of fire, but it is imperative that we pass the gases at high speed to achieve self-cleaning. A critical design parameter is the so-called pinch point temperature in the boiler. Pinch point temperature is typically in the range of 10 to 20 degrees Celsius. Lower pinch temperature means that we get a larger boiler with higher heat transfer area, with higher efficiency, but at the same time with lower gas speeds, which mean higher tendency of soot deposit, and higher pressure drop. Pinch temperature is the minimum temperature difference between the exhaust gases and the saturated steam. Looking at the formula for steam production potential, which is given by MIN, it seems that MIN is optimistic by about 50 to 60%. I want to believe that there is a typo in the formulation. We have to acknowledge gratefully MIN sharing a lot of information from us, and you will see that in this presentation a lot of info comes from MIN. Further to that, the sensitivity of the exhaust gas temperatures and flow rates to the ambient conditions is indicated and has been produced by MN. A blessing in disguise for the new regulation of low sulfur content in fuel is the reduction of the dew point. That means that we can cool now the exhaust gases even further. We can go lower. It is advisable to monitor temperatures upstream and downstream the turbocharger. Because if there are problems, monitoring can indicate, for example, fouling on another problem. Monitoring of temperatures is advisable also in the exhaust gas boiler because we can, for example, see if there is any problem with fouling. We observe a gradual change. A sudden change might indicate a fire. Of course, now in the time of slow steaming, the exhaust gas boiler will operate with exhaust gases of lower flow rate. We expect that the capacity of the boiler to produce steam is affected. So the boiler capacity is definitely decreased. There is dependence in the production of steam from the exhaust gas parameters, namely flow rate and temperature, the feed water temperature, the boiler design and maintenance, and of course, the ambient conditions. In part load operation, we have lower flow rates along with lower fuel consumption, which means lower available thermal energy in the exhaust gases. This also means lower gas velocities, higher propensity for soot deposition, and you notice that the temperature of the gases can actually increase at lower loads of the engine, but what decreases is their flow rates. Looking at the triangle of soot fires, which is a problem in slow steaming, it encompasses the presence of oxygen in the exhaust gases, estimated at around 14%, the source of ignition for the soot, and also soot deposition. A safe bet is to design the boiler for a minimum gas velocity of about 20 meters per second to avoid soot fires. Also, the feed water temperature needs to be boosted in order to avoid wet soot deposition in the tubes. The radical solution, of course, at part load is to bypass the boiler. Further to that, we need to add guide vanes at the entrance of the boiler to ensure that we have a uniform gas velocity. In the way of an example, for a container ship, which follows, as you can see here, the cubic propeller law, the target is to estimate the flow rate of the exhaust gases and their enthalpy. Usually this information is available by the manufacturer, by the maker. If this information is not available, there are ways to estimate it, for example, with the incorporation of air-fuel ratio as a function of load. Now, we can avoid complicated thermodynamic calculations for the exhaust gases by assuming that the exhaust gases are clean air. We can assume that there are no products of combustion. The error because of that assumption is about 2%, fully acceptable. The estimation of the boundary temperatures is based on the pinch point and also the pinch point temperature and also the boiler pressure. Notice that the introduction of very efficient engines these days has resulted to reduction of the temperature downstream the gas turbine, to turbocharger. I was very surprised when I first saw that the temperature downstream the turbine was around 230 to 250 degrees Celsius. This doesn't compare with previous the designs of 10, 20 years ago, when this was about 100 degrees higher. So efficiency, of course, has its price. Having a low temperature downstream the turbine means that we cannot get enough heat in the economizer. The target is to compute the specific gas enthalpy, and running to the final solution, the result is what we expect. The thermal content of the exhaust gases increases as the speed increases. Even more important, if we do a thermodynamic balance calculation, if we equate and compute the thermal energy of the exhaust gases with what we get for the feed water, we obtain the quantity of steam which is generated. Looking at this graph, 5% reduction, 5 knots reduction in the speed of the vessel will result in a reduction of the steam generating capacity of about 50%. It is very critical. These conclusions still hold at various ambient conditions. Here you see the tropical, the winter, and the ISO reference conditions. We see that the trend also remains. Waste heat, of course, reduces a lot with engine load, waste heat recovery, and evidently, as expected, the most critical situation is with winter, under winter conditions for waste heat recovery. As a closing note, it is pointed out that slow steaming practically can be done by doing nothing, do nothing up to 50–55%. This is the magic number below which load percentage we need to activate the auxiliary blowers. That's when they come in. I hope it has become evident that when we contemplate slow steaming, it is necessary to check the steam production capacity of the exhaust gas boiler and potentially look for different sources of heat recovery. Of course, it has to be pointed out that to do something alternative, like to utilize heavy fuel oil instead, it is fully acceptable in maneuvering situations or during channel and river crossing. But it is considered to be a pathological situation in case of sea travel, sea trips. We should not be obliged to fire heavy fuel, oil-fired boilers, in order to produce steam at sea. Thank you very much.